We have previously defined the concepts of velocity and acceleration, with velocity being the rate of change of displacement and acceleration being the rate of change of velocity. In this video, we will look at using these two fundamental definitions to derive a series of formulas or equations. These equations can then be used to describe or to predict the motion of an object. Acceleration can be written as a final velocity minus the initial velocity, divided by the final time minus the initial time. Often, the initial time is taken to be the start of some event, so that the start time is set to 0 and the formula can be simplified. Here, t is taken to be the time duration of the event. In this equation, we can determine the acceleration of an object if we know what the initial and final velocities are and how long it took for the velocity to change. In other instances, we might want to know how fast an object is moving at some later time in the future if we know what its initial velocity and acceleration is during that time. To do that, we can transpose this equation to find the final velocity. Doing so gives us the following equation. Alternatively, we might want to predict how long an object, say a car, takes to accelerate from say 0 to 100 km per hour at a constant rate of acceleration. We could then transpose the equation to give us a formula for time as a function of velocity and acceleration. Let's consider an example. A rescue helicopter is hovering above a broken down boat. It drops a small emergency kit down to the boat. The kit takes 2 seconds to fall to the water. So what is the speed at which the kit hits the water? A practical example of such a question might be if you were to design such an emergency kit, you would want to know if the kit can withstand the impact of hitting the water when dropped at certain heights. So knowing the impact velocity will be important. To answer the question, let's have a look at the facts of the problem. It takes the kit 2 seconds to hit the water. Because the kit was dropped, its initial velocity will be 0. Since the kit is falling vertically downwards, it is experiencing acceleration due to gravity. The magnitude of this acceleration is 9.8 meters per second squared. In this problem, we will ignore air resistance, which might slow the kit down. We will talk more about acceleration due to gravity in a later video. Note that because velocity and acceleration are vectors, we need to define a positive direction. Since the motion is downwards, we'll define going down as positive. This lets us write velocity as a positive number since it's moving in a positive downward direction. Gravity causes objects to accelerate as they fall down, so acceleration is also in the positive direction. We are asked to calculate the velocity when the kits hit the water, so our unknown variable here is the final velocity v. We can now apply the information we know to the equation. Since we are looking for the final velocity, we will use the following form of the equation. We then substitute the values for each known variable, then finally solve the final velocity to give us an answer of 20 meters per second, rounded to 2 significant figures. Now you have a go at these questions. The 2013 Ford Mustang Boss 302 can go from 0 to 100 km per hour in 4.5 seconds. What is its average acceleration during this time? Assuming it can maintain this acceleration, how long will it take to reach its top speed of 259 km per hour from a stationary start? The first equation in our list of equations for motion comes from the definition of acceleration and is written in terms of the final velocity being equal to the initial velocity plus the product of acceleration and time.